And all right, so we're ready to do this problem where we're going to start trying to at least start to estimate the area underneath this curve. You can see the area there in blue for the function 1 minus x squared. And you can see we're looking at the area from 0 out to 1. So what we're going to do is just break this into two sections, and we're going to approximate the area underneath there with rectangles. So the first one I'm going to do is I'm going to draw a rectangle that has a width of 0.5. We'll call this delta x1, and a height here of 1, which just happens to be f of 0 is what equals that 1. And then the next one I'm going to do, I'm going to come to whatever this is right here, and I'm going to go on out to 1. So I'm going to make it into this right there. Again, I'll have this same width here. It's delta x2, we'll call it. It doesn't necessarily have to be the same, but in this case, they will both be the same. And then, of course, this height right here is going to be f of 0.5, whatever that happens to be. So total area, right, if we call this like rectangle 1 and this rectangle 2, our area total is going to be the area of rectangle 1 plus the area of rectangle 2. Now, obviously, you can see that this is going to be a little greater than the blue area, but it gets us kind of a rough idea, at least for going through the motions of doing this. And of course, we can make the rectangle smaller to get more accurate. So, you know, we can do things to make this a little better. So if we look at the area of rectangle 1, it's going to be the same thing as always. It's base times height. So the base is delta x1 times the height, which is f of 0, right? That's regular old base times height. Then and so that's area 1. And then for area 2, it's going to be delta x2 times f of 0.5. Kind of squishing it on there, sorry. And that's going to be area for rectangle 2. If we look at this, delta x1 is simply 0.5. And f of 0, we can see right there from the graph, is just 1. And then for area 2 here, delta x2 is also 0.5. And then we need to figure out what f of 0.5 is. That's just going to be 1 minus, right? We're going to plug it right into here. 1 minus 0.5 squared, just like that. So on the first term, we have 0.5 times 1, which is just 0.5. Then we have a plus here. So in this little part, we have 1 minus 0.5 squared. So it's half of a half, which is 0.5 squared. So that's 0.25. And 1 minus 0.25 is 0.75. And so then we need a half times that. So we're going to end up with 0.5 times 0.75. I prefer to do that with fractions. So I'm going to make this 1/2. And this is 1/2 times 3/4, just a little simpler. And so we end up with 1/2 plus 3/8, just like that. And we can go ahead and try and add those together. We get a common denominator, which is going to be 8. And so to get 2 to be 8, you multiply it by 4. So this is 4/8 plus 3/8, which is just 7/8. And then that right there is our answer for the area inside of those rectangles. It's not exactly the area under the curve. It's going to be something a little bigger than it. But you can see that if we made these rectangles narrower and narrower, we would get closer and closer to this. Doing it in this way, where we end up with something that's greater than the area of our thing, where we kept picking rectangles that started up here at the top and went outside of our function, is what is called an upper sum. Okay, and so that's what we did right there. And on the next page, we will do some other kind of sums. But I'm going to go ahead and pause real quick and see if there are any questions. All right, so let's go ahead and take a look now at the next page here, where we've got this graph a couple of more times, and we're going to try and do the same thing, but we're going to change it up just a little bit to try and get at this. So for this one, what we're going to do this time, instead of breaking it up into into 2 sections, we're going to break it up into 4 sections. So I'm going to look down here at this one, just like this, and I'm going to make some extra little marks here. We're going to do 0.25, and then we'll do 0.75, just like that. And instead of going outside of the curve, we're actually going to stay inside. So when I come up on this side, I'm going to come across this way and do the sum from there underneath the curve. And then I'll do the same thing here and here, and I'll make these into rectangles as well. Okay. And then of course on this last one, it's not really much of a rectangle there. So we're going to try and take this area that's then lower, that's underneath this curve. Okay. And so to do this, we of course need our width. Well, the width of each one of these is 0.25. So our total area is going to be 0.25. So for this first one, it's 0.25 times its height. And its height is going to be f of 0.25, because now we're looking at that point right there. And so its height is f of 0.25, not f of 1. And then we're going to do the same thing for the next one, which will be 0.25. That's our base times our height. This time is right here is f of 0.5 right there. So f of 0.5. And then the next one is going to be looking right here. This is f of 0.75. So this is plus 0.25 times f of 0.75, and I'm kind of running out of room. So, and then a plus, and then this very last one, this is going to be 0.25 and f of 1. So this is 0.25 times f of 1. So now we just need to go through and start figuring out what each one of those is. So f of 0.25 is going to be 1 minus 0.25 squared. So this is 1 minus 1/4 squared. And 1/4 squared is 1/16. And so this is 15/16. And then f of 0.5 is 1/2, which is 1 minus 1/2 squared, which is 1 minus 1/4, which is 3/4. Here we have 1 minus 3/4 squared. And so this is 9/16. So 1 minus 9/16 is going to be 7/16. And then for this last f of 1, which is 1 minus 1 squared, which is just 0. Okay, so we can go through and start plugging these in now. We're going to have 0.25 times 15/16. We're going to have I should have made that 1/4. Let me make that a 1/4, just so we're working with fractions. This is 1/4 times 15/16. This is 1/4 times 3/4. This is 1/4 times 7/16. And then this is 1/4 times 0 for that last one. And all we have to do now is multiply these together and start reducing. So if we start multiplying these together, I did this a little earlier so we don't have to waste our time with all this multiplication stuff. It should be 34/64. That one was a 0. And please feel free to go through and double check me on that one. Each of those can be divided by 2. So this is 17/32. And so what we now know, this is essentially our lower sum. All right, this is our lower sum. And what we know is that our lower sum is less than the actual area, and our upper sum is greater than our actual area. So we know that it has to be somewhere between what we got over here with the 7/8 and what we got here with the 17/32. So this one is definitely less than the area. The other one is definitely more. So we've kind of narrowed it down that it has to be at least somewhere in that group or that range. All right, so after that, we can actually go down here and we have one more way that we can do this. So here, what we're gonna do is we're gonna break it into fourths again. So we're gonna break it into 4 different rectangles. So 0.25, 0.5, 0.75. Now, the last time we took the highest point, we went above the function. And this time after this, so in other words, we took like the left side of the rectangles. Then on the previous one, we just took the right side of the triangles or of the rectangles, which kept us inside the function. So this time what we want to do is take the center of the sections. So this time when I draw my line up this way, what's going to happen is I'm going to come here to the middle. And this is 0.125. And we're going to take that point right there. And then we're going to draw that rectangle in. And so this rectangle is partially inside and underneath. You can see here, like I tried to draw it a little nice there. It's underneath, we're missing that part, but we're also including that part that's outside of it. And so we can do a midpoint version here and do the same thing for this one. We can come up this way, we'll go up a little bit above it, and then you take that middle point right in between them, come up to here and draw that rectangle in. And then you do the same thing here. You come on up, follow this middle point on up, right? Come across, draw it in, and then the same thing here. You come up, come across, just like that. And here you have 4 rectangles, but instead what you're looking at is these different midpoints. And just to make it a little simpler, I'm going to call this C1, this one C2, this one C3. So center 1, center 2, center 3, and then center 0.4. And if you were going to do this one, you would then find the area inside of those, and it would be that same delta. This time it's times f of whatever C1 happens to be, whatever that center point is, plus delta x times f of C2. And you can just kind of keep doing that on all the way to, you know, however many things you divided it up into, okay? And if you do it this way, so we can do like, we can do f of, I'm sorry, we can do delta x times f of C in here, and we can say n is the number of subintervals that you did. So here we did 4, which meant we would have stopped right there. It's your number of subintervals. In the picture there, I did 4, so it would have been 4. And this way is called the midpoint sum, just like that. Okay, so let me pause again real quick, see if there's any questions. All right, so in order to get a better approximation, we'd simply use more subintervals. What we've got here is a table that shows the values, sorry, my dog's shaking his head there, of the upper and lower sum approximations under that area. So if you do 2 subintervals and even the midpoint ones there as well. And you can see that as you keep going to higher and higher subintervals, you see that these numbers get to be closer and closer to each other with the 0.66. So if you get down to this last line, they all agree to the first 2 decimal places at least there, and they're pretty close on that third one, right? And so it gets to be more and more accurate. So we don't have necessarily a way to have calculated this exactly, I guess, exactly, maybe some quotes there. I want to pause for a second. I want you to tell me, just by looking at this chart, what do you think the actual area underneath the curve there, that blue area, is going to turn out to be? All right, we got a good answer there. It sure looks like it's going towards 2/3, 0.6 repeating. So I would say this is looking like 2/3. So even without doing it exactly, you could come in here. You could even make like a computer program or something that would do that right there for you. Okay. Now let's move on to our next page here, and we're going to look at distance traveled. So suppose, well, actually, before we do that, let's define a few little variables here. First, we're going to do S of t, and this is going to be our position at time t. And then what we can have is, if you remember this from calculus 1, we take our first derivative of position, and so in other words, we're getting the change in position, and that's our velocity, right? That's our velocity as a function of time. And then if we take the derivative of velocity, the first time derivative of velocity, we get acceleration. Okay, just as a little reminder of what we had before. If we did one more, which we probably really won't deal with too much and you don't usually deal with a lot, if we did a derivative, a time derivative of acceleration, we get what is called jerk. And that's the rate of change of the rate of change. So velocity is the rate of change of position, acceleration is the rate of change of velocity, and jerk is the rate of change of the acceleration. Okay, so just a quick little reminder there for you. So let's pretend here, suppose we know that the velocity function v of t is 10t minus t squared feet per second of a car that moves straight down a side road without changing direction. How far did the car travel in 3 seconds during the trip? Say t equals 5 to t equals 8. Use the summation techniques from just described to estimate the distance. How close to the sums does it actually come of 66 feet? So I'm going to go ahead and pause here for a moment the recording, and I'm going to let you try and do this. I want you to work out an upper sum and a lower sum like we just did, and then see how they compare to that 66. All right, so as you can see here, this problem was worked out. If you're watching this video later, you can pause it and go through it, but you can see that the actual answer was between both our upper and lower sums there. Okay, so let's move on to this next place. Next page. First, we're going to talk about displacement versus distance. Those are actually two different things. One of them is a vector, that's displacement. The other is a scalar, right? It just scales things, and that is distance. So if you remember before, displacement is the change in position, including the direction of that change. In the previous example, we knew that the car did not turn or change direction, hence displacement and distance traveled were equal-ish. I'm going to put quotes around that equal, because they're still not necessarily equal. One has more information than the other. They're a different mathematical structure, but they were equal. They were basically the same. The magnitude of them, I guess I should say, was equal. If the object changes direction one or more times during the trip, then we need to use the object's speed, zoom in here a little bit, which is the absolute value or the magnitude of the velocity to find the total distance traveled. We have the following equations where n is the number of subintervals. And so what you can see there is in the first one, we're doing displacement, where we're actually worrying about direction of the velocity being traveled. And so there's a direction there. So this one might be forward, this one might be backwards, and then forward, and then forward, and then a backwards or something like that. And so some are adding and some are subtracting, assuming this is one dimensional, or is this just going left and right or something like that? Because you also have one that maybe went up or something like that, or at an angle, and you have to add them up like vectors, and it's kind of difficult. If you're looking for distance traveled, there should be an I there, distance traveled, then you're going to basically just take the absolute value or the magnitude of each of the velocities, which gives you the speed. All right. And then you just take the speed times the time, and you don't worry about this. Where's an example where this would be different? Well, if you're thinking about something like race car driving, right? If you look at race car driving, say maybe like the Indianapolis 500 or something, I think they drive 500 miles on that, going around in circles. Well, when they start, they go all the way around, a whole bunch of times, and they end up right where they start. So their total displacement here in that race is actually 0, because they end up right where they started the race is where they end up at the end of the race. So they have a distance of 400 miles, but they have a displacement of 0 because they're right back where they started during that race. Okay, so that's the difference between the distance and displacement. Displacement cares about direction. It's the straight line distance between where you started and where you ended. And distance, on the other hand, is more like how many steps you took. If you think about, if you ever knew anybody who's from like a mountainy area, they have an old saying called the way the crow flies. So they might say, town A is here and town B is here. And they'll say something like, well, they're 2 miles apart the way the crow flies. And what they mean is that this town in a straight line is 2 miles apart, because if there was a crow flying between the two towns, it would just fly in a straight line. However, if you're in the mountainy area, the roads aren't straight. The roads do something like this and twist and turn all around. So they say, oh, it's, the way the crow flies, it's 2 miles. But when you actually go to drive it, it's more like 5 miles. And so the way the crow flies is more like the displacement. It's just going to go in a straight line. It has no reason to really curve all around. But the actual distance it takes you to drive there is going to be longer than that as you curve all around, and the actual direction doesn't matter. So overall, same displacements, but between those two, that red arrow and the blue line, but 2 different distances there. All right. Now, one more thing we want to look at here is average value of a non-negative continuous function. The average value of a collection of numbers is just add them all up and then dividing by the number that you added up, or the number of them you had. But what is the average value of a continuous function on this? And it's actually pretty similar in idea here. So if we take a look here, not super interested. If you wanted to do the average value of that crazy line down there for the weather forecast, that would be really difficult to do. You might be able to go through and pick out a few points, like evenly space them, and then go through and take an average, but you're not going to get an exact average. It would be an approximation. So what we can do is think about it this way. If you did go through and start picking out points, what if I tried to do the actual value at every single point? So if I came in here and looked at this, and I looked at the value at every single point, it would technically be an infinite number of points from here all the way over to there. But what I can do with that is then divide that. If I go through and add up the values of every single one of those points, what I'm essentially going to get is the area of this, right? Because it's going to be like this plus this plus this plus this plus this. And I'm going to find ultimately the area of that rectangle. And then if I divide it by the number of points that I did, well, the number of points I did is simply from A to B, right? And so I did B minus A across there is that length. So for looking at that first graph in picture A, we can actually do the average. So the average value of it, so the average output, is going to just simply be the area under divided by B minus A. In this case, the area underneath, let's say this is 1 and this is 11, and up here C is equal to 5. Well, then my average value is going to be that area underneath, which is going to be 5, which is the height, times the base, which is 11 minus 1, over top of 11 minus 1, because that's that length I did, which is going to be 5 right there, and that's all that's left, because the 11 minus 1, the 11 minus 1, they cancel. And so in that one, it's pretty straightforward. The average is going to be 5, because that's all the values there, all have that same value. But what about here? What if you look at that next picture B? Would that still work, this same idea? And the answer is yes. You could go through and find all these different little heights here, add them all up, find the area underneath this whole thing, and then divide it by B minus A. So for B, again, in general, our average value, all right, in general, right, is going to be area under divided by the length of the interval. Okay, so that's what this is going to be in general. I probably didn't need that second, though it looks like multiplication, so maybe I'll just take that out here. It's going to be just in general, area under times the length of the interval, and that's going to give you an average value for that function. Okay, so let me pause for a moment and